Hello, welcome to another edition of Cryptic. Last week we took a look at the Diabolical Sudoku from the Telegraph, and I'm going to try and do the same puzzle this week. Well, obviously the diabolical one rather than exactly the same puzzle, but they seem to publish diabolical puzzles on Fridays based off the pattern. You can see last Friday there was the one we did. This Friday, let's take a look and see top times there. Someone's recorded a time of 1 minute 36 seconds. Well, I think we can dismiss that. That's not going to be a real time unless the puzzle's got substantially easier from the one that we tried last time. So we can put in some pencil marks here. Remember the pencil marks that we like to do in any 3x3 box. If a number can only go in one of two positions, exactly two positions in that 3x3 box, then that's what we notate. So that's what the little numbers are going to represent as I go through the solve here. You can see this interesting 2-4-1 combination here. That's probably the first place I'd be focusing on with any seriousness. That's going to give me a few 8s, just by simple Sudoku logic. Put some 8s in there. Where else can we put some 8s? Oh, actually write a big 8 here, so 8s look like the place to start in this puzzle. Again, you can make some pencil mark 9s over here. One thing I would say about Telegraph software for pencil marks is I don't really like having, you see these 9s written into these two cells. They're in exactly the same position as these 1s are, i.e. it's just central. When I make pencil marks when I'm solving with pen and paper, is I would write my pencil marks in the appropriate corners of the square. So I divide each square into 9 sort of a little box. So this top left square would represent a 1, this would represent a 2, this would represent a 3, 4, 5, 6, 7, 8, 9. And that just helps a little bit in terms of speed as we're going through. I almost don't have to interpret the actual shape of the number. I can simply interpret where it sits within its cell. You can see that these pencil mark 3s here give us a 3 here, not a 4, a 3, and that gives us a 3 here as well. So we're off to a better start, I think, than we were last week. 5 and 7 are the open numbers here. You can see we can have pencil mark 7s and 5s, in fact. That's useful. Okay, so now what can we deduce from this? Well, there's exactly two cells that contain a 5 and a 9, these two. Therefore this cell has to be a 7. I'm going to remove the pencil mark 7 from this cell. And let's see what we can do with this. So you can see that there is a 9 in one of these 3 cells, just by using this 9 here, and the fact there's a 9 in either of these 2 cells. But because we don't have any 9s up here and no pencil mark 9s either, I have not allowed, using the notation we're recommending, to write in anything in any of these 3 cells. We just sort of have to remember that. And the 5s might be more useful. If we scan the 5s across and use this 5 here, again, I can make more pencil marks. And that's what we like to do. Now, unfortunately, again, there's no 5s and no 9s at all. So all we've done here is we know that these 3 cells, now 2 of them will be 5 and 9, but we can't go further than that. Can we do anything with... no, we can't. We can see this cell here has to be a 2, just by simple Sudoku rules. That allows us to write more pencil marks up here. Okay. It looks like we might have to look somewhere else to make... I'd probably just check this column because it has 6 digits in it already. So you can see there we need 3, 4 and 6. There's nothing doing in that regard just at this stage. Use 2s here. This 2 scans across, and that means we can write in a 2 here. Not terribly useful, but Should always write in numbers if we can get them. So 4, 6, 7, 9 now in row 6, so the open positions. Again, I'm going to check that just in case there's anything useful. Although 7's ruled out by a couple of 7, these two 7's ruled out 7's from these two positions. These two can still take a 7. Now I remember last week we needed X-wings and all sorts of things to solve it, so I'm going to try and remember that a 7 can go in only one of those two positions. That sometimes can be a way into spotting an X-wing later in the process. And let's carry on. See, this cell here has to be a 7. Let's write that in. That gives us a 7 here as well. And we've got 4, 6, 9 in these 3 cells here. And you should be able to see that actually is going to give us a 6, because we have a 6 here and a 6 here. So that means the only space left for a 6 in this row is here. And this cell now are 4 and 9, and look, there's a 9 here. So we can write in a 4 here and write in a 9 here. That means we can pencil mark in 4s to these two positions. I'm just wondering if I can do anything with the 9. Yes, I can get pencil marks. With that. This box is becoming quite congested now. You can see 3, 4 and 5 are the only available cells, but there's a real dearth of 4s and 5s anywhere in these sort of in the central cross of the grid. We can make some pencil mark 1s over here and 3s actually. Probably check columns 5 and column 6 now, just to see if there's anything. 2, 5, 4, 9 in this. See, this cell is very restricted, but that's the only cell in this column that's seriously restricted, I think. We've already recorded the 2's here. And then 3, 4, 5, 7 for this central column. See again, another double would be appearing here. Some people, that's the notation they like to use. Indeed, some people will use this notation and recording cells that can only be one of 2 numbers if they're solving on paper, because you can record that in a variety of ways, but we don't have that luxury, unfortunately, with the software we're using on the Telegraph site. Or indeed the Time site. All of them don't seem to allow you to make more than one type of pencil mark. Let's see, these 3's over here, those 2 positions, and 6's, this 6, 6, right, 6 in here and 6 in here, that gives us a 6 into this position. Now, can I make it any useful? Yes, I can. If we look over here, because of this 6 here, we've locked a 6 into one of these 2 positions. That means the 6 in this 3x3 box can only go either here or here. So this 6 resolves that ambiguity. Let's write that in. And in turn, that's going to allow us to write in a 6 over here as well. And now, okay, now I think we just need to use our memory, because if I remember correctly, we concluded that a 5 and a 9 was somewhere in this bottom row. You can see, we can just double check that quickly. A 9, a 9, so there's a 9 in the bottom row, a 5 and a 5, so there's a 5 in the bottom row, and now look, we have a 6 and a 6, so there is also a 6 in this bottom row. In fact, the 6 must go here, but by simple Sudoku rules, which means that these 2 cells have to be 5 and 9, and look, we have a 9 here. So that's a 9, and that's a 5, which means these 2 cells are 4 and 7 in some order. Let's put those in. 7 and 4. That means this has to be a 5. And now we're at a stage where we just have to be careful, because it's very easy we've just got a lot of new information into the grid, and what we've got to make sure that we do is use it all, because it would be a shame not to. See that this, we need an 8 in column 4 here. It can't go here, it has to go here. 8, 9, like that. That resolves the position of an 8 over here. Just move that 8. Now, is this 9 any use? Not really. Well, I say that. How many unknowns have we identified here? We've got 1, 3, 4 and 6. Oh, so it is useful. So we can see if we use the 9 here and the 9 here, well, in fact, just use the 9 here. This means that the 9 in this 3 by 3 box is in one of these 5 cells. In fact, it's in one of these 3 cells because of the presence of the 9 here. Now, does this matter? Yes, because now look what's happened. If there is a 9 in one of these 5 cells, we also have a 1 in one of these 5 cells, a 3, a 4 and a 6. So there are 5 unknowns in these 5 cells, exactly. And that means this cell here must be the other number, the number we haven't even thought of to check yet in this box. So this number has to be a 5. Let's write that in. I think that will be useful. It will be. So we can now write a 5 here and a 2 here. Now that 2 must give us some pencil marks, I imagine. Yes, it does. We've got 4 and 7 in these 2 positions. That's resolved like that. This is a 3, 4 in the central column. 7's over here. This row here, we need a 2 in one of these 2 positions, which, so now I'd be, in fact we can just write a 7 in here. I should have spotted that more quickly. That's a 7 over here. Let's remove that 7. So now this has to be, one of these 2 has to be a 4. So, a quick look at this line, 4, 5, 9. Can't quite see how to use that yet. Oh, of course we've got this 5 now, so that's going to resolve this 5, 9 combination down here. Further limits the positions a 9 can go in this top box here. Nearly done now, I think. 2, 4, 1 or 4, 2 or 4. And if we have a look at this box here, there's a nice pattern you can see. So there's a 5 and a 9 here in these 2 positions, and a 5 and a 9 here. Now that means that these 2 cells have to be 1 and 4, because they can't be 5 or 9. And 5 or 9 we need to put in the box somewhere, so the 5, 9 combination is here. 5, 9 like that. Okay, now what could we do? We might be able to use something I've seen before in these diabolical puzzles. Let's have a look at this box and just see. So what I'm looking at, just so that you guys know, is I've noticed that in all of the open cells that we've concentrated on, so ignore this 3 by 3 box, everything is a choice of 2 numbers. Yeah, every cell, we've done the work, and you can see immediately just by quickly looking at the grid that every cell that's unsolved, if you like, is a choice of two numbers. Now, I think I remember that there is a principle in order for you to have a unique solution to a Sudoku. It is impossible that every cell in the puzzle that is unsolved contains exactly two solutions or two numbers that are open, because in that situation you'll basically find the solution is not unique. So if we look at this cell, we've got to put 2, 4 and 9 in it. So 9 can go here or here, and 4 at the moment is open, I think, isn't it? It's the 4 that we have to resolve. So this cell can be, I'm going to slightly break with my notation in order to show you the principle I'm thinking about here. This cell can be a 2 or a 4, this can be a 4 or a 9, and this cell can be a 2, 4 or a 9. Okay, now I think the way this worked was that you need to choose the number here such that in effect these three cells form a triple. Any other choice will result in a problem, and I think it's going to be quite interesting actually for us to prove that. So here you can see there's a 4, 9, there's a 2, 4, so I would this cell you can eliminate the 2 and the 9, i.e. the things that would form the triple. I think we'll find this cell here has to be a 4 when we work through the solution. Now, to prove that to you, okay, and we're going to interrupt the solve now because I did waffle on for a while, trying to explain by reference to the puzzle I was actually solving how this sort of bug principle works, but it got incredibly complex, and I rewatched the video and thought it wasn't going to be understandable. So what I did was I did some research on the forums, located from 2005, and I'll put the link in the video, some discussion on one of the Sudoku forums about this sort of pattern, this pattern where you can conceivably end up with situations where every open cell, if you like, is a choice of two number, and how that can lead to a non-unique solution. And this particular puzzle here was posted as an example back in 2005 by somebody called Nick67. I'm not sure who that is. I used to know a solver called Nick Dello, who's a very good Sudoku solver and logician. So it could be him. It could be someone else too, obviously. But I thought this was quite an elegant way of showing why this sort of pattern can lead to a problem. So you can see here, this is a Sudoku, all of the options are labelled, and the only position here where we have a, if you like, a choice of 3 rather than 2 numbers is in this cell. And what I'm going to do is, you can see also, I think, very quickly that if a 9 was eliminated from this cell, so it was 2, 5 possibility, then this cell would immediately resolve itself. Yeah, and in resolving itself, the whole puzzle could still be forced out, in the sense that if this was just a choice of a 2 or a 5, then there wouldn't be the situation where every cell in the puzzle is a choice of 2 numbers, because this cell would not be a choice of 2 numbers anymore. This cell would be forced to be a 9. Okay, so we break this principle that we're trying to establish. So in fact, the only situation where this cell could legitimately be a choice of 2 numbers and leave every other cell a choice of 2 numbers as well is if we eliminate the 2 as a possibility here. So if this was a choice of a 5 or a 9, you can see that doesn't resolve anything in this box. So what I want to imagine is that this 2 isn't valid here. and this is a choice of a 5 or a 9. And now I'm going to try slowly to show how that can lead to a problem. So if we assume this can be a 5 or a 9, let's just go through the puzzle. Let's just force a solution out. So let's just make this cell a 2 and see how that impacts on the solve. So this would be a 2, this would be a 4, 4, 9. Now this was a 5, 9 choice, so that is forced to now be a 5. This is a 9, this is a 2, 5, 2, 9, 2. This has to be a 9, this has to be a 5, this has to be... In fact, that's not going to work. It's not going to resolve itself down here. We've got 2 9s in the same. And now we need to do a little bit of a sort of a feat of imagination, if you like. So having said that this is a 5 or a 9 choice, let's imagine that the Sudoku was suddenly solved. Okay, so imagine we're now looking at the Sudoku and it has a completed solve with all of these optional squares filled in some order. Okay, and now what we need to imagine that we do, let's just look at this box here. Let's imagine that whichever order this 2, 4 are in our completed solution, we swap them. Okay, so this was a 2 and this was a 4. I want us to imagine that we swap them over. So this would be a 4 and this would be a 2. And now let's imagine what happens as a result of this switch that we've just done up here. What happens to the grid? It should be pretty obvious that the first thing that would happen is that the values of this cell would switch as well. So this would switch round, and then the effect of this switching round would be to switch these middle 2 over as well. Because the switching of the 4s here switches the 4s here, which also switches the 9s, which then switches the 9s here. Now the effect of switching the 9s here is that it switches the 5s over here, which would switch the 5s over here. Now the effect of switching the 5s over here has an effect on this box up here now. So if in our if before we did all these switches, this was part of the valid solution, you should be able to see that this would have been a 9. Now we said this was a 5 or a 9, so this would have been the pattern in this top right 3x3 box, if this 2, 4 combination was valid. So what I'm going to do now, let's remember this, let's just swap these over, if the machine will let me. Oops. Let's make this the 4, and this the 2, this the 9, this the 4, this the 2, this the 5, and this the 9. And you can see that in fact the effect of all these shufflings is that you would have 2 solutions to the puzzle, because every time you're swapping a pair, you're swapping a number out of a row or column, but the effect of swapping it out of a column is that you swap that number back in to the row or column immediately, just by looking at the next box, because we saw how as we propagated round the grid, we were simply swapping numbers over. So that is my attempt at trying to illustrate in a simple example like this one, why if you get to a situation where everything is a choice of 2 numbers, you effectively, by switching 2 of the numbers over, you immediately just swap round the grid, and what I think one of 3 things will happen. Either you'll get a repeated digit in a row, or a repeated digit in a column, or you'll get another solution to the puzzle, all of which are obviously problematic. So what we need to do, in fact, is to avoid this situation. We know that given that puzzles published in our daily press will have been probably either computer created or created by someone in test solved, they won't have they won't have more than one solution. So we can use the fact that the solution is unique to make choices that avoid this sort of situation arising. So how do we do that in this position? Well, the only way of doing that is going to be to select a value here that, that basically forces this not to happen. And we know if this is a choice of a 5 or a 9, we have a problem. The only way to avoid this being a choice of a 5 or a 9 is to force it to be a 2. And by forcing it to be a 2, the puzzle will solve. But for the purpose of this puzzle, all I have to do is say, I don't want this situation to arise. The way I do it is by thinking about what triple I could create and making sure, and then picking the other number. So here, I knew this needed to be a 4, and once I've done that, the whole thing flows.